So hello friends, in the previous video we have discussed the frequency response of 5 transistor OTA on the transistor level, where what we have seen that the major contributor to the pole is your load capacitance CL. Okay, so what I mean to say, this CL is contributing to the load. When we are considering this GM cell as the ideal GM cell, then there is a pole at origin. The response for that is this, and we have seen this thing already. And when I'm considering that my GM cell is offering some finite impedance, output impedance at this node, in that sense, what we can see, there is a finite output impedance which is nothing but RDS of 2 parallel with the RDS of 4. And this calculation we have seen in detail because exactly it is not like that directly to saying the output impedance to RDS2 and parallel with RDS4. Rather, it is some complicated circuit. What we have seen an equivalent impedance looking at terminal X and how it is affecting it, and then we have seen the total output looking impedance, and with that output impedance we got this pole frequency. Okay, so the point is that let I'm considering there is a no other pole, so let consider it as a one pole system. Okay, so which is the generally we have the we always think to design a first order system as a one pole system, because for the first order system there is a good stability margins and phase margin is good, we can say. Okay, so let's consider it as a first order system where your omega p, or I can also say omega p1, is nothing but 1 upon r out CL. What is the R out that we have seen? RDS2 parallel of RDS4, and CL is already a load capacitance, which is some higher capacitance. So what transfer function exactly for the first order system we define as the A naught divided by 1 plus S by omega p. The omega p, so the 3D frequency, this is a 3D frequency, that is omega p, and A naught is the DC gain that we have seen already from here. The DC gain for any particular block or structure, the GMR out, that thing we have seen already many times. And GM for the 5 transistor OTA structure comes nothing but minus GM of 1, 2. That we can directly see after the short circuiting the output, and we can calculate the short circuit output current divided by this input voltage, differential input voltage. We can have this GM that is always comes for GM of 1, 2, or the input transistor pairs GM only. This is my GM of the computer structure. And R out we already have calculated in the previous video is this. So what is the gain? Gain is nothing but GM12 times this R out, which is nothing but RDS2 parallel RDS4. Okay. So from here we can see the transfer function, which is the first order transfer function, is coming like this. And for that, we have seen the calculation of omega UGB. So what is the omega UGB? The definition of omega UGB is well clear, which is the 3D frequency times DC gain. And the 3D frequency we have 1 upon R out DCL cross GM12 R out. So R out are cancelled. So GM12 by CL is the UGB frequency. So what we have seen, any general GM cell, whether it is an ideal means there is a no load or the infinite load looking from the outside, means output terminal of this GM cell, or whether it is a practical GM cell, the UGB is going to be same. The things which are going to be changed here all like gain and 3 dB frequency. So we can see this is the ideal case, the upper one where we are having this linear line cutting the y-axis and x-axis. In this, we have seen that 3D frequency is 0, and ideally the gain is infinite. Okay, and for the practical case, when we are considering the R out is non-infinite or some finite value, there is a finite gain and finite 3 dB frequency also, which is nothing but omega p. Okay, and after that both the curves are coinciding, and omega UGB, which is nothing but GM by CL, GM of that particular GM cell, which is nothing but a GM of the input pair. So this is the discussion that I want to make here. If I'm considering it as a one pole system, then this is the all about the first order system that we have seen already. Now let's consider the capacitances at node Y and X also. Okay, so now come at this place. So what is happening here? Okay, one thing that I should clear here, I already have designed the PPT. Now I'll explain through this Miss laser pointer, so that in the lesser time we can cover a lot of things. Okay, So what is happening here? At node Y, I have a capacitance associated with this node is Cy, and there is a node X. Because whenever we see to calculate the poles, we have to see the whatever possible nodes in that particular structure. So this is one node, this is one node, and this is another node. Okay. So overall, what I can see, there one pole we have already calculated for the load capacitance. Now we are looking for the pole contributed by this means Y node, and there is a X node as well. Okay, so what is the net capacitance at Cy node? It is nothing but CG3, gate of 3 transistor, gate of 4 transistor cap, and cap of drain of first transistor, this is M1. So what we are seeing, this node is shorted, there is a diode connection. So my Y node is seeing 3 capacitances at a time. We can also say that CG3 means I can write it CGG also, and CGG is a general representation that we can see in cadence that I already mentioned here. So CGC is nothing but total caps associated with the gate. Same, the CDD is nothing but total caps associated with the drain. So what is the CY then? CY then can be written as CGG3 plus CGG4 plus CDD1. Okay, so this is the total caps contributed at the CY node. Now, why I'm worrying about these caps? Because what we are seeing, the CGG3 and CGG4 are the gate capacitances, and value of these capacitances is much higher than any other node capacitance like a drain capacitance or source to body or whatever the capacitance is. Gate capacitance has some higher value. The reason for that is very clear, because CGG is nothing but some like CGG is formed by some terms like oxide capacitance multiplied by area is a WL, and this overdrive capacitance is multiplied by some del L times W. So what we can see in general for the device, when there is a high W or L, then we can see there is a large gate capacitance associated with that. So in general, what is there? C oxide capacitance and C overdrive capacitance are the per unit area, or some caps are also per unit length, which are the sidewall cap in this substrate part. I'm not going in detail in the device physics, but okay. For a time being, I can draw a model, which is nothing but a MOS structure. Here we can see what this particular these N wells, let I say it is a NPN. So these N wells and this gate oxide had some overlapping length that I call the del L. So due to this del L, so this is inside this space the width is W that I mentioned. Inside this space, this width is W and this is my length. And some overlapped part I call del L this side, del L this side. Okay. So del L times W is the area for the overlap cap, and L times W is the area for the oxide cap. Okay, so these are the caps where there is a direct involvement of area of gate, which is nothing but W or L, W cross L or W cross del L. Okay, so what we can see in general for a device, when the gate capacitances are coming into the picture, that particular node cap is going to be larger. That we have seen, and already I means mentioned this thing here using this model, and you can go in detail whenever there is a W or L increasing, or for the structure we always say that the gate capacitance is increasing. That's why we always keep the lower means we always try to optimize the area so that the gate capacitances can be controlled majorly. Other capacitances are also involved with the area, but the gate capacitance has the more impact of the area. Okay, so what we have mentioned here, at any node where gates of the devices are involved, caps associated with that node is always greater than caps associated with any other node. The same thing that I already told you. Okay, gate area is directly involved here. And so, from why I am discussing this thing? Because I want to see the first non-dominant pole. Okay, I want to see the first non-dominant pole. We all know that Cl is much higher than any parasitic cap, so the pole contributed by Cl is already at very low frequency, so it is a dominant pole. Okay, so this is my dominant pole, which we already calculated due to the load cap. Now I am looking the first non-dominant pole, then second non-dominant pole. So apart from this Cl cap, there are two other caps at the nodes. There is Cx cap and Cy cap. So as I can say, Cy cap is much higher than the Cx cap because the gate caps are involved, no gate caps is involved here. So what I can see, first non-dominant pole is contributed by your Cy, which is the node that we are looking at, the Y node. And second non-dominant pole is coming due to the x. So I have written here omega p2, which is nothing but pole contributed by the node y, and omega p3, which is nothing but frequency of pole contributed by the node x. Okay, so what are the non-dominant poles are very far because they are coming due to parasitic caps only. So this point you should keep in the mind. Whether I'm considering here what is the non-dominant pole and what the zero, but it is not that necessary here because already we can see the non-dominant poles are very far. Because when we see the omega u, which is the UDP frequency, is nothing but Gm by Cl. As Cl is a large cap, so omega UJV itself is a small number. Okay, and omega 3dB is very small. So in that sense, we can see the parasitic caps are responsible for the non-dominant poles. The non-dominant poles are very far, while the dominant pole is coming due to Cl, so it is a small number. Okay, that thing we can see. Omega u is this number, and ideally, what we expect. This is the our expectation also. Here, these omega p2 and omega p3 are the due to parasitics only, so they are already very far from this omega u. But in some design, when you will design some higher order means amplifiers or op amps, means second two-stage op amp, three-stage op amp, or the multiple stage op amps, then we can see the pole frequencies coming due to the other structure of this complete design maybe lesser than this omega u also. Okay, so our target is that always we should keep this omega p2 or omega p3 or any other non-dominant pole far from this omega UGB so that we can have the first order response at least till the omega UGB frequency. And we know that for the first order system there is a nice phase margin, hence good stability there. Okay, so this is the ideal expectation, but in this case, we are seeing that omega p2 and omega p3 will be far away because they are only they are means coming due to the parasitic caps. Okay, so all dominant poles should be away from UGB. That is the point or our design. This is okay for better phase margin, for better stability. So ideally, we always try to design a first order system at least around the omega UGB. So omega okay, so omega p1 is the only pole yeah, at least around the omega UGB so that we can have the better phase margin. Now, what we are seeing in this structure, omega p1 is the only pole before UGB. Okay, so omega p1 is a much smaller than the UGB that we can see from here because UGB is nothing but Gm by Cl while omega u is nothing but GDS by what does it say? GDS by Cl, and GDS is a smaller than what I should say. Yeah. So what is the GDS? GDS of that particular transistor is much smaller than its. Okay, so I should say one thing here. Okay, yeah. So what we can see the omega u is the number Gm of transistor 1 comma 2 divided by Cl, while what is omega P1 or I will study omega 3 dB is what? GDS of what I should say 2 plus GDS of 4. Okay, GDS 4 divided by Cl. So in general we see that any GDS is much smaller than the GM. Ideally this is a thing. Okay, so from that viewpoint we can see the omega P is much smaller than this omega mu, and omega P2 and omega P3 are away from this omega UGB. Okay, so this is our expectation. Rather, I should say they are far away because they are contributed by the parasitics. I am again and again focusing this thing here. At least non-dominant poles should be away by the magnitude of 10, or if they are 10 times or 2 times, 4 times, it is better. At least they should be means away from this my omega mu with a factor of 10 is good thing. Otherwise, any number is fine, like 2 times, 4 times, 5 times, but they should be away from that omega u. Now the other thing, that is 0. Zero should also come into the picture because in this 5 transistor OTA structure, what we are seeing, there are two paths from input to output. Okay, this thing I will mention later. So there is a possibility of zero as well, and where this zero lie, we will see in the coming calculations. Okay, now we will see the pole calculation here due to this CY node. So what we can see, the CY has the capacitance CGG3 plus CGG4 plus CGD1 we already seen. So sometimes I have used a small CG and sometimes I capital G. So it is nothing but a gate capacitance only. Okay. So yeah, parasitic caps that we expect that omega P2 should be very greater than omega P1. This is already omega P2 is nothing but pole contributed by this Y node, and Cy is much lesser than Cl. The frequency at which omega P2 is going to come, Cl should be sorted. So this is the point. I'll tell about this point in detail. Let's wait. So what I mean to say, Cy is the node cap at this particular node, and now I want to see the output impedance or the node impedance looking in this Y terminal. Okay, so I have applied a same the current source here IT, and I am observing the VT voltage, and there VT by RT is going to be R by, and from that we can see what is the pole. Pole is nothing but 1 upon R by Cy at the node Y. Okay. So one thing is there, what I told here, the frequency at which omega P2 is going to come, CL should be sorted. So what we are seeing, the omega P2 is coming due to the parasitics. So it is going to come at very higher frequency than omega P1 or the pole contributed by the CL. So when we are analyzing our circuit at that high frequency, our CL should be sorted. So for the time being, I am considering my CL is not sorted. So what is happening here? Okay, let we should see it. So what is this IT current which is coming into this node has two paths. One is a I3, one is a I1. Okay, and one thing we already have seen many times or in the previous video, this I1 current has two paths now. One is this M0 side and other is the source of M2. So it will follow the source of M2. So let this I1 is completely going here and this I1 is approaching to this way and it is finally going to this transistor M4 is a I1. Let's say it is not shorted or there is a no current flowing in the output terminal. Okay, let I am considering it is not shorted. Then what will happen? What will happen? This I1 is equal to I3. From here we can see. And what is the I3 now? Okay, so this thing we have seen I3 equal to I1 as my complete I1 is folding here and going to I3. And one more thing we should see here, this I3 current which is flowing through the M3 is also copying in this M4 terminal. So what is the total current then flowing in the M4 terminal is nothing but I1 plus I3 and it is the same current that is also coming yeah, that is coming from this IT terminal. Sorry, this IT is nothing but a sum of these two currents only, I1 and I3. So my I1 equal to I3 because the same current is flowing in this, or I should say, yeah. If I'm considering it is not sorted, then I1 is also flowing in this, and I3 is also flowing in this. So at that time, what should I say? I1 should equal to I3. Okay, this is the point because I3 is copying to M4 as well. So from here, what we can see, okay, now I should calculate what is the I3 because my IT is nothing but I1 plus I3. So I3 is nothing but IDS3, whether it is a PMOS or NMOS, I will always write IDS3. It is nothing but GM3 VGS plus some terms of GDS which I am not writing here. So GM3, what is VG? VG here is my nothing but a VT only, and source is at means ground. So what we can see, I3 is nothing but GM3 VT. So from this expression we have written here I3 is GM3 VT and I3 is also equal to I1. So what is the IT? From here IT equal to I1 plus I3. So IT is going to be 2I3 which is equal to 2 GM3 VT. So what is the impedance in this node when we are applied this current source? This impedance is nothing but 1 upon 2 GM. So 1 upon 2 GM. So what should be there? From this particular viewpoint, if I am seeing what is my RY is nothing but 1 upon 2 GM3 and CY already there. So what is the pole value? Pole value is nothing but 1 upon CY RY which is coming as 2 GM3 by CY. But it is not actual answer. The actual answer of pole is this GM3 by CY. Then why this 2 factor is coming extra? The 2 factor is only coming extra due to we are considering that cap is not shorted and no current is going toward the output terminal or the complete current I1 is folding back and coming to this M4, then this case is arriving, we are getting the pole frequency at 2 GM3 by Cy. But actual, this is the answer, GM3 by Cy. How it will come, we can see. Now, what we have seen previously, this impedance, or I should say, yeah. So, what actual this should be the answer? We can see from here. If this is, let's say, shorted, then what should happen? Actually, okay. So, this thing I mentioned here, let my this terminal is shorted, so whatever the amount of current I1 is flowing this way should go to this shorted path, and whatever the I3 is coming this way should come from I3, or should also come from the shorted path, or this from the ground itself. Okay, so now we'll see what is the exactly I1 and what is the I3. Okay, so let me see one thing here. Okay, let's see one thing here. What is happening? Actually, the I1 should be 0 and I3 is a non-zero value which is equal to IT only. So why I1 should be 0, that I can say here. Okay, so what we are seeing from this structure, if I am considering this half side of this particular structure, then top side is nothing but this is a M3 which is offering the, when we are looking up the RD3. RD3 means when we are looking in the drain of M3 transition comes nearly 1 upon GM3. And what to speak of RD1? So before speaking about the RD1, let is what is happening at this node. So this node has two impedances approx. This is a 1 upon GM2. This calculation we have seen in the previous video itself, and 1 upon RDS naught. So parallel of these two resistances is coming at the source of this transistor M1, which we have seen. It is nothing but resultant. Effectively, it is 1 upon GM2. So when we are looking from this RD1 terminal, what we are seeing is RDS1 times GM1 times 1 upon GM2 is the approximate resistance looking down in the drain of this transistor M1. Okay, so what we can see when we are looking up the RD3, the impedance is nothing but 1 upon GM3, and when we are looking down, the impedance is nothing but 1 upon GM2 times this intrinsic impedance. So this intrinsic impedance of transistor 1 is of order of few tens or hundreds, with order of 100 maybe. So in that sense, what we can see, the impedance that we are looking down is very large than the impedance looking up. So what we can see, RD3 is much smaller than the RD1. So effectively, I can say that my IT current is completely flowing toward this I3, which is nothing but IT itself is equal to I3 and I1 is 0. So from here, what I can say, IT is nothing but GM3 VT. So VT by IT is nothing but RY is equal to 1 upon GM3. And when we put this value here, what will get, the omega P2 will get as a GM3 by CY, which is the desired result we have seen here. This is the actual pole value at the mirror node. Okay. So due to mirror, there are two parts of the output, so there is a possibility of zero as well. Okay. So we have seen the calculation of zero. So one may think that why this I1 is zero. So you can see in that sense. Okay, so you can see the yeah, this impedance looking down is much higher, or exactly you can apply the voltage division as well. So this is my, sorry, current division, this is my IT. Okay, so one impedance it is seeing is my RD1, which is much higher, and other impedance it is seeing is the order of, is my RD3. So it is the order of 1 upon GM. It is the of the order of some gain, intrinsic gain times 1 upon the order of Gm, 1 upon Gm. So you can say if my A is approx 100, or it is of that order, Gm RDS of the transistor 1, then you can say the complete current IT will flow this way and the no current component will go this way. Okay, so this is the only concept I tried to explain here, and from that we can see this is my pole frequency desired pole frequency at node Y. Okay, so this is the desired pole frequency. Y. So Now, yes, okay. So this is the way of exact analysis of pole calculation. Directly is saying that with anything we cannot intuitively say here, but yes, if you have good analysis, then you can say directly that the impedance looking in this node should be of order of 1 upon gm3 only, because there are two transistors connected this way. So this is looking some high impedance branch, so this branch is looking some high impedance branch because there is a lot of things connected down, and we are looking at the I mean drain of this transistor M1, and upper side is nothing but it is looking at a simple 1 upon of the order of 1 upon Gm. So ideally directly anyone can say the impedance here Ry is of the order of 1 upon Gm3. So this is the only intuition, and Cy already we know. So the pole frequency we can say the Gm3 by Cy. Okay, so this is the directly with the intuition we can say, but we must have the idea of this exact calculation, what is happening at this node and why this current and why this output cap is considered as a shorted. This thing is very important. Why shorted? Because we are analyzing our circuit and some higher frequencies where this node load cap is nearly shorted. So we can say that exactly whatever the amount of current, whether it is copying here to here with M3 to M4, the copied current, which is I3, is coming from this ground terminal. Okay, and ideally the I0 is going here, and whether some amount is going here, it will completely go to this means ground itself. It will not going to flow across the I4. Okay, so I have considered ideally I1 to be 0. If even it is a non-zero value, it will follow this path only. It is not going to flow through this M4, and whatever the amount of current I3 getting from here is also coming from I3, oh sorry, from the ground. Okay, so you can see this analysis in detail, and you can do this analysis by your own. Now apart from this pole, what we can see, there is a possibility of zero as well, because the output has two paths. Here we have output, and the output has two paths, one path directly coming from m1 to m2, and one path is due to this mirror. Okay, so due to mirror there is a possibility, there are two paths of the output, so there is a possibility of zero as well. Okay, so we can see directly, if there are two paths between input and output, then by shorting the output we can have the zero contribution here, and this thing we have seen many times. When we see this output to be 0 for the calculation of 0, then what we can say, current I1 plus I2 equal to total I should be 0. So I1 plus I2 equal to I should be 0. From here what I can say, I1 equal to minus of I2. What is the I1? I1 is your V1 by Z1. What is your I2? V in by Z2, because we are already we are considered 0. So what we can see, Z1 equal to minus of Z2 is the responsible combination for existing 0. Combination of two path impedances. Two path impedances for the existence of 0. Okay, so this is the way, and the zero analysis we will see in the next video. In the next video, we will exactly calculate the zero, and we will see some interesting things when we will calculate the zero. Okay, so as of now, it is enough the discussion of first non-dominant pole, which is the pole contributed by the node Y, and exactly we can see the ways of calculation of the impedance looking at the node Y, and from there we can get this pole. Okay, and we also discussed some sort of device physics here. If you want to know more about this MOS cap or the capacitors which are involved with the MOS, the overlap caps or whatever the offside caps, so what is happening with these caps at different voltage value when we are applying at the gate to source terminal, then what exactly is the variation? If you want these things to be detailed, then you can ask me, or then you can post in the comment section. We'll discuss these things in detail as well. Okay, so this is enough for this video. Thank you.